If you're watching this, consider expanding to full screen. Let the frame fill your vision. And if this journey resonates with you, subscribe. There's more to explore. Now, let the light dim around you, and let's begin. A slow drift through space. No music, only the faint suggestion of distance. There's a tendency, when we look upward on a clear night, to imagine that the universe we see is representative of the universe that exists. We observe points of light, steady and familiar, and we construct from them a picture of order, of constancy, of worlds that might, in some distant echo, resemble our own. This is not a fault of imagination. It is a limitation of perspective. The universe does not present itself to us as it truly is. It filters itself through atmosphere, through distance, through the narrow band of radiation our eyes can detect. What we perceive as the cosmos is, in fact, a carefully edited version of reality, stripped of its most violent, most alien, most unimaginable characteristics. Earth has taught us, through the long education of our senses, that planets are spheres of rock or gas, that they orbit stars at distances conducive to stability, that they possess atmospheres, perhaps, or moons, perhaps, or seasons that turn with gentle regularity. We have built our understanding of planetary science on a sample size of 8, 9, if we're generous with history, and for most of human existence, we believe these 8 to be the totality of planets that existed anywhere. It was a reasonable assumption, given the data available. It was also extraordinarily, almost incomprehensibly, wrong. The first planet discovered beyond our solar system, confirmed, measured, analyzed, was not a world of green fields or distant mountain ranges. It was not a pale blue dot suspended in a sunbeam. It was a thing called 51 Pegasi b, detected in 1995 through the subtle wobble it induced in its parent star, and it defied every expectation we had constructed about how planets form, where they reside, and what they can become. This world, later designated as a hot Jupiter, orbits its star at a distance closer than Mercury orbits our sun. It completes a full year in just over 4 Earth days. Its atmosphere, if it could be called that, is heated to temperatures exceeding 1,000 degrees Celsius. It is a gas giant, massive and bloated, existing in a place where no gas giant, according to our models, should be able to form. The discovery was not celebrated immediately. It was doubted. Some astronomers suggested the data was flawed, that the wobble was caused by something else, stellar activity, perhaps, or instrumental error. Others proposed that the planet had formed farther out and migrated inward, dragged by gravitational interactions with the protoplanetary disk from which it emerged. This latter explanation turned out to be correct, but the implication was profound. If planets could migrate, if the solar system's architecture was not fixed at birth but could be reshaped by time and gravity, then the diversity of planetary systems was not constrained by initial conditions alone. It was dynamic, evolutionary, capable of producing configurations we had never imagined. And so the floodgates opened. Within a decade, hundreds of exoplanets were discovered. Within 2 decades, thousands. Each new detection expanded the taxonomy of worlds, revealing categories of planets that had no analogs in our solar system, that existed in environments so extreme they seemed to violate the principles of planetary science as we understood them. We discovered worlds orbiting so close to their stars that their surfaces were molten, their atmospheres stripped away by stellar wind. We discovered worlds so far from their stars that they drifted in eternal twilight, their surfaces frozen into landscapes of exotic ices. We discovered worlds that did not orbit stars at all, rogue planets cast out from their birth systems, wandering the galaxy in solitude. We discovered worlds around dead stars, around binary stars, around stars that pulsed with such violence they should have incinerated any planetary system in their vicinity. The universe, it turned out, was not lacking in planets. It was overflowing with them. Current estimates suggest there are more planets in the Milky Way than there are stars, perhaps as many as 400 billion worlds, each one a distinct experiment in physics, chemistry, and time. And among this unimaginable multitude, the vast majority are nothing like Earth. They are not habitable. They are not temperate. They are not gentle. They are extremes made solid, laboratories of nature where the fundamental forces that govern matter are pushed to their absolute limits. Consider the nature of heat. On Earth, heat is a manageable phenomenon. Our planet orbits the Sun at a distance of roughly 150 million kilometers, receiving a flux of solar radiation that warms the surface to an average temperature of 15 degrees Celsius. This energy drives weather, evaporates oceans, sustains ecosystems. It is abundant, but not overwhelming. There are places on Earth where heat becomes oppressive, deserts where surface temperatures exceed 50 degrees, volcanic regions where magma breaches the crust, but these are localized exceptions. The planet as a whole exists in thermal equilibrium, radiating away as much energy as it receives, maintaining a stable climate over geological timescales. Now consider a planet orbiting its star at a distance of 5 million kilometers. Now 150 million. 5 million. This is closer than Mercury, closer than any planet in our solar system. At this distance, the stellar flux is not measured in gentle watts per square meter, but in overwhelming kilojoules, enough to heat the surface of a rocky world to temperatures exceeding 2,000 degrees Celsius. At such temperatures, rock itself begins to behave like a fluid. Silicates vaporize. Iron melts. The distinction between solid ground and atmosphere becomes ambiguous, as the surface radiates heat into a sky filled with vaporized minerals, creating clouds of molten rock that condense and fall back as rain. These worlds exist. They are called lava planets or magma ocean worlds, and they represent one of the most extreme categories of exoplanets yet discovered. The prototypical example is a planet designated K2-141b, a super-Earth orbiting a distant orange dwarf star. This world is tidally locked, meaning one hemisphere perpetually faces the star while the other remains in eternal darkness. The dayside temperature reaches 3,000 degrees Celsius, hot enough to vaporize rock entirely. The night side, by contrast, plunges to negative 200 degrees Celsius, cold enough to freeze the same vaporized rock into solid form. Between these two extremes, there is no gradual transition. There is a terminator line, a boundary where day meets night, and along this line, the physics of the planet becomes truly alien. On the day side, the surface is an ocean of molten lava, hundreds of kilometers deep. This is not a metaphor. It is a literal ocean with waves and currents driven by the extreme heat and the gravitational pull of the star. The lava is composed primarily of silicates, silicon, oxygen, magnesium, iron, elements that on Earth form solid rock, but here exist in a state of permanent liquidity. The ocean is so hot that its surface evaporates continuously, feeding an atmosphere of vaporized rock. This atmosphere is not thin or insubstantial. It is dense, opaque, filled with supersonic winds that carry the vaporized material from the day side to the night side at speeds exceeding 5,000 kilometers per hour. As this vapor travels across the terminator into the night side, it cools rapidly. The temperature drops by thousands of degrees over a distance of mere kilometers. The vapor condenses into liquid droplets, which then solidify into tiny fragments of rock suspended in the air. These fragments fall as precipitation, literal rain composed of molten silicates, hardening as they descend through the cooling atmosphere. When they strike the night side surface, they accumulate into vast plains of rocky debris, piled high by eons of deposition. But this debris does not remain stationary. The night side is colder than the day side, creating a pressure gradient that drives surface currents. The accumulated rock flows slowly back toward the day side, completing a cycle. It is a weather system, but instead of water cycling through evaporation and precipitation, it is rock itself that cycles, sublimating on the day side, condensing on the night side, flowing back to begin again. This process has no analog on Earth. Our planet has weather systems driven by water, carbon dioxide, nitrogen, substances that transition between solid, liquid, and gas at temperatures we consider normal. But K2-141b operates on a different scale entirely. Its weather is geology in motion. Its geology a form of meteorology. The planet has seasons, but they are not caused by axial tilt. They're caused by the eccentricity of the orbit, which varies the distance from the star over the course of each year. When the planet is at periastron, closest approach, the day side heats even further and the lava ocean swells. When it is at a pastron, farthest distance, the ocean cools slightly and the night side claims a greater share of the surface. Over time, measured in millions of years, this cycle may drive a slow oscillation in the planet's climate, a breathing in and out of heat that reshapes the surface with each exhalation. But K2-141b is not unique. It is one member of a broader class, and within that class, there is variation, gradation, a spectrum of extremes. Some lava planets are smaller, retaining less heat, their surfaces cooling just enough to form a thin crust that cracks and reforms in tectonic convulsions. Others are larger, their gravity so intense that the lava ocean is compressed into exotic states of matter, where pressure forces the liquid into crystalline structures that should not exist. Still others orbit stars that are older, cooler, their heat output waning, and these worlds are in the process of freezing, their lava oceans solidifying from the night side inward, locking their geology into a permanent record of the temperatures they once endured. The existence of these worlds forces a reconsideration of what we mean by the term planet. On Earth, we think of planets as objects with solid surfaces, stable over time, upon which chemistry can occur, life can emerge, history can accumulate. But a lava planet has no stable surface. Its crust is transient, reformed daily by the cycling of heat. Chemistry, in a conventional sense, cannot occur there. Molecules cannot persist long enough to react, to bond, to build complexity. The only chemistry that occurs is the thermodynamics of phase transitions, solid to liquid, liquid to gas, gas to solid, driven by heat and pressure alone. These are not worlds where anything we would recognize as life could exist. They are not worlds where complexity can accumulate. They are, in a very real sense, planets reduced to their most fundamental processes, stripped of all emergent properties, laid bare as engines of heat transfer and nothing more. And yet, they are not without interest. They teach us about the limits of planetary formation, about the conditions under which rocky planets can retain atmospheres, about the long-term evolution of worlds subjected to extreme stellar radiation. They serve as laboratories for studying the behavior of materials under conditions we cannot replicate on Earth, where pressures reach millions of atmospheres and temperatures exceed the boiling points of every element in the periodic table. They are, in their own way, as informative as any potentially habitable world, because they reveal the boundaries of the possible. Thermal extremes, however, are only one axis along which planets can diverge from familiarity. Consider now the role of orbital mechanics, the gravitational dance that determines not just where a planet resides, but how it experiences time itself. Tidal locking is a phenomenon well known in our solar system. The moon is tidally locked to Earth, presenting the same face to us at all times. Mercury is in a spin-orbit resonance with the Sun, rotating 3 times for every 2 orbits. These configurations arise from gravitational interactions over long timescales. A planet close to its star experiences a stronger gravitational pull on its near side than on its far side, creating a tidal bulge. This bulge exerts a torque on the planet's rotation, gradually slowing it until the rotation period matches the orbital period. At that point, the planet is locked, one side forever facing the star, the other forever facing away. For a planet like Earth, tidal locking would be catastrophic. Our rotation period is 24 hours, far shorter than our orbital period of 1 year. If Earth were tidally locked to the Sun, one hemisphere would bake under perpetual daylight while the other froze in perpetual darkness. Winds of unimaginable violence would scream across the terminator, attempting to equalize the temperature gradient. Oceans, if they remained liquid, would migrate toward the substellar point, piling up under the star's gravity. The planet's climate would collapse into a configuration unrecognizable to us. But Earth orbits far from the Sun, and tidal locking requires proximity. For planets discovered in the habitable zones of red dwarf stars, small, cool stars that constitute the majority of stellar types in the galaxy, tidal locking is not just likely, but inevitable. Red dwarfs are so dim that their habitable zones lie extremely close in, often within 10 million kilometers. At such distances, tidal forces are powerful, and the timescale for tidal locking is measured in millions, not billions of years. Every planet in the habitable zone of a red dwarf is expected to be tidally locked, presenting the same face to the star for the entirety of its existence. This has profound implications for habitability. A tidally locked planet does not have a day-night cycle. It does not have seasons, unless its orbit is eccentric. It does not have the regular turnover of heat that drives Earth's weather systems. Instead, it has permanent day and permanent night, two hemispheres with radically different climates. The day side, heated continuously, could become a desert, its water evaporated into the atmosphere. The night side, cooled continuously, could become a frozen wasteland, its water locked into ice caps that never melt. The planet's atmosphere, if it is thick enough, might transport heat from the day side to the night side, creating a narrow band of temperate conditions along the terminator. This band, neither day nor night, could be the only region where liquid water persists, where temperatures remain within the range life requires. But this assumes the atmosphere survives. Red dwarfs are violent stars, prone to flares that release as much energy in minutes as they emit in weeks. These flares produce intense bursts of ultraviolet and X-ray radiation, which strike the planet's atmosphere and strip away lighter molecules, hydrogen, helium, water vapor. Over time, a planet in the habitable zone of a red dwarf may lose its atmosphere entirely, reduced to a barren rock with no protection from the star's radiation. This process is especially severe for tidally locked worlds, because the same hemisphere is always exposed, always receiving the full brunt of each flare. There is no rotation to distribute the damage, no night side to serve as a refuge. Some tidally locked planets may survive this onslaught. If the planet is massive enough, its gravity can retain a thick atmosphere despite the stellar wind. If the star is old enough, its flaring may have subsided, allowing the planet's atmosphere to stabilize. If the planet formed with abundant volatiles, water, carbon dioxide, nitrogen, it may have enough reserves to replenish what is lost. But these are contingencies, not certainties. For every tidally locked planet that retains its atmosphere, there may be dozens that do not. They're scoured down to bare rock, their surfaces sterilized by radiation, their potential for life extinguished before it ever begins. And even among those that do retain atmospheres, the climates are strange beyond terrestrial experience. Consider a world we might call Proxima Centauri b, orbiting the nearest star to our Sun. This planet is approximately Earth-sized, and it resides within the habitable zone of its red dwarf host. It is tidally locked, with an orbital period of just over 11 days. Simulations of its climate suggest the day side could be warm, perhaps even hot, with surface temperatures exceeding 50 degrees Celsius at the substellar point. The night side, by contrast, could plunge to negative 100 degrees or colder. Between these extremes, along the terminator, there may be a ring of temperate conditions, a twilight zone where the temperature hovers around freezing, where liquid water could pool in shadowed valleys, where an atmosphere thick enough to redistribute heat might create perpetual twilight, neither bright nor dark. But this is speculation, built on models that assume certain atmospheric compositions, certain surface properties, certain distributions of land and water. We do not know if Proxima Centauri b has an atmosphere. We do not know if it has water. We do not know if its surface is rock, ice, or something else entirely. What we do know is that it represents a category of planet that is extraordinarily common in the galaxy, small rocky worlds orbiting red dwarfs, tidally locked, bathed in radiation, and that if life is to be found beyond Earth, it may well be found on worlds like this, in configurations that bear no resemblance to the planet we evolved on. Tidal locking, however, is only one way orbital mechanics can shape a planet's experience of time. Consider now the case of a planet in an elliptical orbit, where the distance from a star varies dramatically over the course of a year. In our solar system, planetary orbits are nearly circular. Earth's orbit has an eccentricity of just 0.017, meaning the difference between its closest and farthest approach to the Sun is negligible, only a few million kilometers. This near circularity ensures that Earth receives a relatively constant flux of solar energy throughout the year. Seasons are caused by axial tilt, not by distance. But many exoplanets have highly eccentric orbits, with eccentricities of 0.3, 0.5, even 0.9 or higher. These worlds experience dramatic swings in stellar flux over the course of their years. At perihastron, they plunge close to the star, receiving intense heating. At apastron, they recede to great distances, where the star's warmth is barely felt. The result is a climate that oscillates wildly, a world that transitions between extremes with each orbit. Take, for example, a hypothetical planet with an eccentricity of 0.6 orbiting a Sun-like star. At perihastron, the planet might receive 3 times the solar flux Earth receives, heating the surface to temperatures where water boils, where atmospheric pressure spikes, where storms of extraordinary violence erupt. At apastron, the flux drops to 1/3 of Earth's, and the planet cools rapidly, water freezing, atmospheric pressure collapsing, the surface falling into a state resembling a snowball Earth event. Over the course of a single year, perhaps lasting several Earth years, the planet cycles between these states. Life, if it existed on such a world, would need to survive both extremes, adapting to heat and cold in rapid succession, or else migrating across the surface in pursuit of a narrow band of habitability that shifts with the planet's position in its orbit. Such planets are not rare. Among the exoplanets discovered, eccentric orbits are common, particularly in systems where gravitational interactions between multiple planets have perturbed their trajectories. These worlds are inhospitable by any measure we apply to Earth, but they are not sterile. They contain liquid water, at least part of the time. They have atmospheres, though those atmospheres may condense and sublime with the seasons. They undergo chemistry, weathering, erosion. They are dynamic, evolving, complex. They are planets in every sense of the word, even if they bear no resemblance to the world we know. The question of what makes a planet habitable, then, becomes not a binary classification, but a spectrum. Habitability is not a property a planet possesses or lacks. It is a function of time, of location, of the specific biochemistry we are asking to support. A planet that is uninhabitable for complex multicellular life might be perfectly suitable for extremophile microbes. A planet that is uninhabitable today might have been habitable a billion years ago, or might become habitable a billion years hence. A planet that is uninhabitable on average might have pockets of habitability, subsurface oceans, volcanic vents, sheltered valleys, where conditions allow chemistry to proceed toward complexity. This realization has shifted the focus of astrobiology from finding Earth-like planets to finding planets where liquid water can exist, where energy is available, where organic chemistry can occur. It has expanded the catalog of potentially habitable worlds far beyond what was imagined when the search for exoplanets began. It has also forced a recognition that habitability, by itself, is not sufficient to produce life. Earth has been habitable for 4 billion years, and for most of that time, life was simple, single-celled, confined to oceans and soils. The emergence of complexity, of multicellularity, of intelligence required not just habitable conditions, but stable habitable conditions, sustained over geological timescales, with sufficient environmental variability to drive evolution, but not so much variability as to extinguish nascent ecosystems before they could take root. Most planets do not provide this stability. Most planets are subjected to forces that render their surfaces hostile to complexity, if not to chemistry itself. And among the forces that shape planets, few are more dramatic, more violent, more transformative than the presence of a massive atmosphere and the weather systems it generates. Gas giants are not, in the strictest sense, planets with surfaces. They are planets that are atmosphere all the way down, with no solid crust to stand upon, no ocean to sail, no ground to till. They are composed primarily of hydrogen and helium, the lightest elements, accumulated during the planet's formation from the protoplanetary disk. In our solar system, Jupiter and Saturn exemplify this category. Massive worlds with atmospheres thousands of kilometers deep, where pressure and temperature increase with depth until the hydrogen itself transitions into a metallic state, electrically conductive, generating powerful magnetic fields. But gas giants and other star systems are not necessarily like Jupiter. They can be much larger, much hotter, much stranger. They can orbit so close to their stars that their atmospheres are heated to temperatures exceeding 2,000 degrees Celsius, where the chemistry of the upper layers is dominated by ionized metals, sodium, potassium, iron, vaporized and suspended in the air. These worlds are called hot Jupiters, and they represent a category of planet that does not exist in our solar system, that was not predicted by theory, that defies many of the assumptions we held about how gas giants form and where they reside. On a hot Jupiter, the atmospheric conditions are extreme by any measure. The temperature gradient from the day side to the night side can exceed 1,000 degrees, driving winds that circle the planet at supersonic speeds. These winds do not blow in simple patterns from day to night and back again. They form complex jet streams, vortices, storm systems that persist for decades or centuries, powered by the immense heat flux from the star. The dayside atmosphere is so hot that molecules dissociate into atoms, and even atoms are ionized, stripped of electrons. The night side, though cooler, is still hot enough to vaporize most substances we think of as solid. There is no liquid water on a hot Jupiter. There are no oceans. There is no surface. There is only gas, heated to incandescence, swirling in patterns determined by the interplay of rotation, stellar radiation, and gravity. But within this maelstrom, there is chemistry. The upper atmosphere of a hot Jupiter contains clouds, not of water vapor, but of exotic materials, silicate dust, corundum perovskite. These clouds form at altitudes where the temperature drops below the condensation point of the vaporized minerals, and they give the planet its color, its reflectivity, its spectrum as observed from distant telescopes. On some hot Jupiters, the day side is clear, the clouds having evaporated entirely, while the night side is shrouded in dense hazes. On others, the clouds form bands, encircling the planet at specific latitudes, driven by the same Coriolis forces that create Jupiter's iconic stripes. And on some hot Jupiters, the clouds produce precipitation. Not rain, in the sense we understand it, but something far stranger. On a planet designated HD 189733b, located 63 light-years from Earth, the atmosphere contains clouds of silicate particles, tiny grains of glass, suspended in the air. The extreme winds blow these particles across the dayside at speeds exceeding 7,000 kilometers per hour, fast enough to shred any material, fast enough to create a perpetual storm of glass shards flying horizontally through the atmosphere. This is not a weather phenomenon we have any experience with. It is not a storm that passes. It is the permanent state of the planet's atmosphere, a howling chaos of heat and wind and shattered minerals, where visibility is measured in meters, where anything exposed to the open air would be abraded to nothing in seconds. HD 189733b is a deep blue color, as observed by the Hubble Space Telescope. But this blue is not the blue of water or sky. It is the blue of scattered light interacting with the silicate particles, a false color that evokes familiarity while concealing profound alienness. The planet is, by every metric, a hellscape, a world where no spacecraft could survive entry, where no probe could descend to measure the deeper layers, where the very concept of exploration seems futile. And yet, it is not without interest. It teaches us about atmospheric dynamics under extreme conditions, about the behavior of materials at high temperatures and pressures, about the limits of planetary science as a discipline. It is a data point in the vast catalog of exoplanets, one of thousands, each contributing to our understanding of what planets can be. But not all gas giants are hot. Some orbit at distances comparable to Jupiter's orbit around the Sun, receiving far less stellar radiation, remaining cold and dark. These cold gas giants are less well studied because they are harder to detect. They do not transit their stars because their orbital periods are measured in years or decades, and transit surveys require multiple transits to confirm detection. They do not produce large radial velocity signals because they orbit far from their stars, where their gravitational influence is diluted. They are found primarily through direct imaging, using large telescopes and adaptive optics to block out the star's light and photograph the planet itself. A technique that works only for planets that are young, still glowing with the heat of their formation, and orbiting at wide separations. These cold gas giants may have atmospheres that are more stable, less violent than their hot counterparts. They may have clouds of water ice, ammonia ice, methane ice, materials that condense at the low temperatures found far from a star. They may have weather systems that are slow and stately, driven by internal heat rather than stellar radiation. They may have moons captured during their formation, orbiting in complex resonances, tidally heated, potentially harboring subsurface oceans where life could emerge. They are, in many ways, analogs to Jupiter and Saturn, but existing in other star systems, around other suns, under different conditions of formation and evolution. And then there are the gas giants that do not orbit stars at all. Rogue planets, or free-floating planets, are worlds that have been ejected from their birth systems, cast out into interstellar space by gravitational interactions during the chaotic early phases of planetary formation. They drift through the galaxy alone, unbound to any star, receiving no light except the faint glow of distant galaxies, no heat except the residual warmth from their formation and the slow decay of radioactive elements in their cores. These planets are extraordinarily difficult to detect because they emit no light of their own, except in the infrared from their cooling interiors, and because they are not silhouetted against a star during transit. They are found, when they're found at all, through gravitational microlensing, a technique that detects the brief magnification of a background star's light as the rogue planet passes in front of it. Current estimates suggest there may be billions of rogue planets in the Milky Way, possibly outnumbering stars. Most are likely gas giants, ejected early in their system's history, but some may be rocky worlds, smaller than Earth, frozen into icy silence. A rogue planet does not have days because there is no sun to mark time. It does not have seasons because there is no orbit to modulate climate. It does not have weather in the conventional sense because there is no external energy source to drive atmospheric circulation. It is a world in stasis, cooling slowly over trillions of years, its surface temperature approaching the cosmic microwave background radiation, the faint afterglow of the Big Bang, which permeates all of space at a temperature of 2.7 Kelvin. And yet, a rogue planet is not entirely dead. If it is massive enough, if it retained a thick atmosphere during its ejection, that atmosphere can act as an insulating blanket, trapping the planet's internal heat. A gas giant rogue planet may retain a warm interior for billions of years, radiating heat outward through its atmosphere, maintaining a temperature gradient that could, in principle, drive convection, create clouds, produce storms. These storms would be faint, slow, invisible to any observer, but they would be real, a weather system powered not by a star, but by the planet's own residual heat. For a rocky rogue planet, the possibilities are even more speculative. If the planet formed with a thick atmosphere, rich in hydrogen, that atmosphere could create a greenhouse effect strong enough to keep the surface above the freezing point of water, even in the absence of a star. If the planet has a molten core, radioactive decay could generate heat, driving volcanic activity, releasing gases that replenish the atmosphere. If the planet has subsurface oceans, insulated by kilometers of ice, those oceans could remain liquid for billions of years, warmed by geothermal heat, potentially hosting chemosynthetic ecosystems that draw energy not from light, but from chemical reactions at hydrothermal vents. This is all speculation, but it is speculation grounded in physics. Rogue planets are not just curiosities. They are laboratories for studying planetary science in the absence of stellar radiation, for understanding how atmospheres evolve in isolation, for exploring the limits of habitability. They challenge the assumption that life requires a star, that planets must orbit in the habitable zone to support chemistry. They expand the parameter space in which we search for life, forcing us to consider environments we had not thought to examine. But rogue planets, for all their strangeness, are still recognizably planets. They're objects with atmospheres, with interiors, with structure. They're not the most extreme worlds the universe has produced. For that, we must turn our attention to planets that orbit not living stars, but the remnants of dead ones. Pulsars are the collapsed cores of massive stars that have undergone supernova explosions. They are extraordinarily dense, composed primarily of neutrons, compressed to densities where a single teaspoon of pulsar material would have a mass of 1 billion tons. They rotate rapidly, often spinning hundreds of times per second, and they emit beams of radio waves from their magnetic poles. As the pulsar rotates, these beams sweep across space like a lighthouse, and if Earth happens to lie in the path of the beam, we detect regular pulses of radio emission, hence the name. Pulsars are not environments where planets should exist. The supernova that created the pulsar would have destroyed any pre-existing planetary system, incinerating planets, blasting them into interstellar space, leaving nothing behind. And yet, planets have been found orbiting pulsars. The first confirmed exoplanets ever discovered were not around a sun-like star, but around a pulsar designated PSR B1257+12, detected in 1992 through precise timing of the pulsar's radio pulses. These planets cause minute variations in the arrival time of the pulses, delays measured in microseconds. But those delays are consistent, repeatable, unmistakable. 3 planets orbit this pulsar, ranging in mass from lunar to terrestrial, circling the dead star at distances comparable to the inner solar system. How these planets came to be is uncertain. They could be second-generation planets, formed from the debris of the supernova, accreting from the disk of material that fell back onto the neutron star after the explosion. They could be the remnants of a companion star, tidally disrupted by the pulsar's gravity, its outer layers stripped away, its core surviving as a planet-sized object. They could be captured planets, originally formed in another system, passing close enough to the pulsar to be gravitationally bound. Each explanation has difficulties, but the planets exist, and their existence demands an explanation. The environment around a pulsar is unlike anything found around a main sequence star. The pulsar emits intense radiation, not in the form of visible light, but as high-energy particles and electromagnetic waves, X-rays, gamma rays, radio waves. This radiation bathes the orbiting planets continuously, stripping away any atmospheres they might have possessed, sterilizing their surfaces, rendering them barren. The magnetic field of the pulsar is trillions of times stronger than Earth's, powerful enough to align the motion of charged particles, to create auroras of unimaginable intensity, to induce electric currents in any conductive material on the planet's surface. A pulsar planet does not experience day and night in any conventional sense. The pulsar emits radiation isotropically from its surface, so the planet is illuminated equally from all sides, or rather, it is bombarded equally from all sides by radiation that is not light, but something far more energetic. The planet's surface is scoured by this radiation, heated not by thermal flux, but by ionization, by the direct transfer of energy from high-energy particles to the atoms in the crust. The temperature of the surface depends on the distance from the pulsar, but it is not a temperature that corresponds to anything we would recognize as climate. It is a temperature determined by equilibrium between the energy deposited by the pulsar's radiation and the energy radiated away as blackbody emission. These planets are not habitable. They are not temperate. They are not places where chemistry, as we understand it, can occur. They are remnants, fossils of planetary systems that once were subjected to conditions so extreme that they erase any history the planets might have had. And yet, they are not without scientific value. They allow us to study planetary dynamics in the presence of strong magnetic fields, to understand how planets respond to high-energy radiation, to explore the limits of what we call a planet. There are stranger planets still, planets that orbit binary stars, where the concept of year is complicated by the fact that the planet is gravitationally influenced by two stars, not one. Planets that orbit in the habitable zone of such binaries, receiving light from two suns, experiencing eclipses and double shadows, their seasons determined by the complex interplay of two orbital periods. Planets that orbit so close to their binary stars that they are simultaneously tidally locked to both, their rotation rates synchronized to the binary's orbital period, their surfaces divided not into day and night, but into regions illuminated by one star, by both stars, by neither. There are planets around stars that are themselves unusual, stars that are metal-poor, formed in the early universe before the first generations of stars had synthesized the heavy elements necessary for rocky planet formation. Stars that are metal-rich, formed from the debris of supernovae, enriched with iron, silicon, carbon, oxygen. Stars that are variable, pulsating in brightness, their luminosity changing over hours or days, subjecting their planets to cycles of heat and cold that repeat far faster than any seasonal variation. Stars that are in binary systems so close they exchange material, transferring gas from one star to the other, creating an accretion disk that engulfs the orbits of any inner planets. And there are planets whose compositions are unlike anything found in our solar system. Carbon planets, for instance, worlds that formed in regions of the protoplanetary disk rich in carbon relative to oxygen. In such environments, the chemistry of planet formation is fundamentally different. On Earth, and on rocky planets generally, silicon and oxygen combine to form silicates, the minerals that constitute the bulk of the crust and mantle. But if carbon is more abundant than oxygen, carbon-bearing compounds take precedence. Carbides form instead of silicates. Graphite, diamond, silicon carbide. These are the materials that make up a carbon planet's interior. The surface, if it is cool enough, might be covered in tarry hydrocarbons, organic molecules polymerized into complex structures, giving the planet a dark, oily appearance. Such planets have not been conclusively identified, but they are predicted by theory, and they may be common around certain types of stars. They would have different thermal properties than silicate-based worlds, different seismic activity, different volcanism. If they have atmospheres, those atmospheres might be rich in methane, carbon monoxide, and other carbon-bearing gases, rather than the nitrogen and oxygen that dominate Earth's air. They would be alien not just in appearance, but in their fundamental chemistry, in the way their geology operates, in the processes that shape their surfaces over time. Then there are ocean worlds, planets where water constitutes a significant fraction of the total mass. In our solar system, Europa, Enceladus, and other icy moons are suspected of harboring subsurface oceans. But these are moons, not planets, and their oceans are covered by thick shells of ice. An ocean world, as the term is used in exoplanetary science, is a planet where the ocean is global, deep, and possibly exposed at the surface. Such planets might form far from their stars, where water ice is abundant, and then migrate inward into warmer regions where the ice melts to form a liquid ocean hundreds or even thousands of kilometers deep. At the base of such an ocean, the pressure would be immense, millions of atmospheres, enough to compress water into exotic ice phases, Ice 7, Ice X, that remain solid despite high temperatures. The planet's rocky core, if it has one, would be buried beneath this ice, insulated from the ocean above, its heat unable to escape except through slow conduction. The ocean itself would be layered, stratified by temperature and salinity, with currents driven not by wind, as on Earth, but by thermal convection and the planet's rotation. There would be no continents, no islands, no land of any kind. The surface would be water from pole to pole, interrupted only by ice flows if the planet is far enough from its star, or by evaporation and cloud cover if it is closer. Life in such an ocean would face challenges unknown on Earth. There would be no shallow coastal zones, no tidal pools, no nutrient-rich estuaries where organic molecules can concentrate. The ocean would be oligotrophic, nutrient-poor, with energy sources limited to geothermal heat from the rocky core and perhaps chemical reactions at the ice-water interface. Photosynthesis would be impossible unless the planet has a thin enough atmosphere and clear enough water for sunlight to penetrate to useful depths. Any life that emerged would likely be chemosynthetic, drawing energy from chemical gradients rather than light, similar to the ecosystems found at Earth's deep-sea hydrothermal vents. But an ocean world, despite these challenges, is not a sterile world. Water is a solvent, a medium in which chemistry can occur, a substance that, in liquid form, allows molecules to move, to interact, to build complexity. An ocean world may be more habitable, in some respects, than a rocky planet with only surface water. The ocean insulates the planet from temperature extremes, moderates climate, distributes heat evenly across the globe. It is a stable environment, changing slowly over geological time, providing the kind of long-term stability that life, or at least complex life, seems to require. And then, at the opposite extreme, there are worlds where water is absent, where the surface is not rock or ice, but something else entirely. Metallic planets, for instance, where the mantle and crust have been stripped away by collisions or evaporation, leaving behind the bare iron core. In our solar system, Mercury is thought to have an unusually large core relative to its size, possibly the result of a giant impact early in its history that blew away much of its rocky mantle. But Mercury still has a mantle, still has a crust. A true metallic planet would be core only, a sphere of iron and nickel, perhaps partially molten, perhaps solid, depending on its mass and the amount of residual heat. Such a planet would have unusual properties. Its density would be high, much higher than Earth's, perhaps 9 or 10 grams per cubic centimeter. Its surface would be reflective, shiny, capable of scattering light like polished metal. It would have no atmosphere, or only a transient atmosphere of vaporized metals, generated by the intense heat of stellar radiation if the planet orbits close to its star. It would be geologically active if its interior is molten, with tectonic processes driven by the cooling and solidification of the core. It would be, in many ways, the simplest kind of planet, composed of a single material, lacking the layered structure, core, mantle, crust, that characterizes most rocky worlds. The existence of such planets is still hypothetical, but there are candidates. Some exoplanets have densities that are difficult to explain unless they are unusually metal-rich, unless they have lost their rocky mantles and are exposing their cores to space. These planets, if confirmed, would represent yet another category in the taxonomy of worlds, another extreme in the spectrum of planetary compositions. And what of planets that are not extreme in any one property, but in the combination of properties? Super-Earths, for instance, rocky planets with masses several times that of Earth. These are among the most common types of exoplanets discovered, yet they have no analog in our solar system. They are too small to be gas giants, too large to be terrestrial planets, as we understand the term. Their interiors are subjected to pressures that, on Earth, are found only deep within the mantle, pressures that force minerals into high-density crystal structures, that alter the behavior of rock, that may drive forms of tectonics unlike anything we observe. A super-Earth with 3 times Earth's mass would have a surface gravity roughly 1.5 times ours, enough to make walking difficult but not impossible. Its atmosphere, if it retained one, would be thicker, denser, capable of retaining heat more efficiently, creating a stronger greenhouse effect. Its geology would be more vigorous, its interior hotter, its volcanic activity more frequent. But it would also be more resistant to cooling, its larger size giving it a greater reservoir of heat, allowing plate tectonics to persist for longer, perhaps indefinitely. Such a planet could, in theory, be more habitable than Earth, its stable climate and active geology providing conditions conducive to the emergence and evolution of life. But super-Earths can also be less habitable. If they form with thick hydrogen-helium atmospheres, inherited from the protoplanetary disk, those atmospheres may never be lost, even under intense stellar radiation. The planet would then resemble a mini-Neptune, a rocky core surrounded by a gas envelope thousands of kilometers thick, with no solid surface accessible from space. Life, if it existed, would be confined to the deep atmosphere, floating in the clouds, drawing energy from lightning or photochemistry, never touching solid ground. The diversity of super-Earths is vast, encompassing planets that are rocky, icy, gaseous, or some combination thereof. They can orbit close to their stars, tidally locked, their surfaces molten or far from their stars, frozen into ice balls. They can have atmospheres composed of nitrogen, carbon dioxide, water vapor, methane, hydrogen, or exotic combinations we have not yet imagined. They are, in many ways, the most important category of exoplanets because they are common, because they are diverse, and because they occupy the size range where rocky planets transition into gas planets, where the processes that govern planetary formation and evolution are least understood. And among the super-Earths, there are worlds that challenge our definitions even further. Planets with surfaces covered entirely in diamond, formed in carbon-rich environments, their crusts composed of crystalline carbon rather than silicate rock. Planets with atmospheres so thick that the surface pressure exceeds that of Venus, where carbon dioxide is compressed into a supercritical fluid, neither liquid nor gas, filling the lower atmosphere like an ocean. Planets where the surface is perpetually shrouded in clouds, where the ground is never visible from space, where rain falls continuously, not water, but sulfuric acid, hydrochloric acid, or stranger substances still. Venus itself, though a planet in our own solar system, is an extreme world by any measure. Its surface temperature is 460 degrees Celsius, hot enough to melt lead, maintained by a runaway greenhouse effect driven by a thick atmosphere of carbon dioxide. The atmospheric pressure at the surface is 92 times Earth's, equivalent to the pressure found at a depth of 1 kilometer beneath Earth's oceans. The air is toxic, corrosive, filled with sulfuric acid droplets that fall as rain but evaporate before reaching the ground. The surface is volcanic, geologically young, resurfaced within the last few 100 million years by massive eruptions that covered the planet in lava flows. Venus may represent the fate of Earth. If our planet's climate continues to warm, if feedback mechanisms push it past a tipping point into a runaway greenhouse. Or it may represent a distinct evolutionary path, a planet that was never habitable, that formed with too much carbon dioxide, too little water, and too close to the sun to ever develop the conditions necessary for life. Either way, Venus serves as a reminder that planets in the habitable zone, as traditionally defined, are not necessarily habitable. The habitable zone is a region where liquid water can exist on a planet's surface, given the right atmospheric conditions. But atmospheric conditions are not guaranteed. They are contingent, dependent on the planet's formation, its volcanic activity, its ability to retain volatiles over billions of years. And there are many Venus-like planets among the exoplanets discovered. Rocky worlds slightly larger than Earth, orbiting slightly closer to their stars, with thick atmospheres and surface temperatures that preclude liquid water. These planets are not habitable, not as we understand the term, but they're not devoid of interest. They teach us about atmospheric dynamics, about the greenhouse effect, about the conditions under which a planet can transition from habitable to hellish. They serve as warnings, as reminders that habitability is fragile, that the conditions that allow life to emerge and persist are rare and easily disrupted. But not all extreme planets are hostile. Some are extreme in ways that make them more, not less, conducive to life. Planets with strong magnetic fields, for instance, which shield their surfaces from stellar radiation, preventing atmospheric loss, protecting potential biospheres from the sterilizing effects of cosmic rays and solar wind. Planets with large moons, which stabilize the axial tilt, preventing chaotic variations in climate, ensuring that seasons are regular and predictable over geological timescales. Planets with active plate tectonics, which recycle carbon dioxide between the atmosphere and the crust, regulating the greenhouse effect, maintaining a stable climate even as the star's luminosity increases over billions of years. These are not extreme planets in the sense of being hostile. They are extreme in the sense of being optimally configured for habitability, of possessing combinations of properties that, by chance or by the vagaries of formation, create environments where life can not only emerge but thrive, where evolution can proceed over billions of years, where complexity can accumulate without being reset by catastrophic events. Such planets may be rare, but they are not impossible. They may exist somewhere in the galaxy, waiting to be discovered, worlds that are not just habitable, but better than Earth, more stable, more resilient, more conducive to the long-term survival of biospheres. The search for such planets is ongoing. Telescopes, both on the ground and in space, are surveying the sky, detecting exoplanets by the thousands, characterizing their atmospheres, measuring their masses and radii, inferring their compositions. Spectrographs analyze the light passing through exoplanet atmospheres during transits, searching for the signatures of water vapor, oxygen, methane, molecules that, in the right combinations, might indicate the presence of life. Interferometers, still in development, promise to image exoplanets directly, to photograph their surfaces, to map their continents and oceans, if they have them, to search for seasonal variations, for weather patterns, for any sign of activity that cannot be explained by geology alone. But the search is not easy. Exoplanets are faint, distant, often overwhelmed by the light of their parent stars. Even the largest ground-based telescopes can barely resolve them as points of light, let alone discern details of their surfaces or atmospheres. The data is indirect, statistical, requiring careful analysis to separate signal from noise. False positives are common. Confirmation requires multiple observations, cross-checks with different instruments, years of patient data collection. And even when a planet is confirmed, characterizing it is difficult. We can measure its mass, its radius, its orbital period. We can infer its density, its surface temperature, its likely composition. But we cannot, with current technology, observe its surface directly, cannot send probes to explore it, cannot answer the questions that matter most. Does it have water? Does it have an atmosphere? Is it geologically active? Does it harbor life? These questions will require the next generation of instruments. Telescopes with mirrors tens of meters in diameter, capable of collecting enough light to analyze the spectra of Earth-sized planets in the habitable zones of nearby stars. Space-based observatories, freed from the distortions of Earth's atmosphere, capable of imaging exoplanets with resolution sufficient to detect continents, oceans, ice caps. Star shades and coronagraphs, designed to block out the star's light, allowing the faint reflected light of the planet to be seen. Missions that will take decades to build, to launch, to operate, but that will, for the first time, give us the ability to study exoplanets in detail, to move beyond detection and characterization toward understanding. And what will we find? The expectation, based on the data we have so far, is that the galaxy is filled with planets, that nearly every star hosts at least one, that the diversity of worlds is limited only by the laws of physics and the constraints of formation. We will find planets that resemble Earth in size, in composition, in climate. We will find planets that are utterly alien, that defy our expectations, that expand our conception of what a planet can be. We will find planets that are habitable, that have liquid water, that undergo chemistry complex enough to produce the precursors of life. And perhaps, though this is far from certain, we will find planets where life has already emerged, where evolution has proceeded along pathways different from our own, where biospheres have adapted to conditions we would consider extreme, where intelligence, if it exists at all, looks out at the universe from a vantage point unlike anything we have experienced. The discovery of life beyond Earth would be transformative, not just for science, but for philosophy, for culture, for our understanding of our place in the cosmos. It would answer one of the oldest questions humanity has asked. Are we alone? But it would also raise new questions, questions we cannot yet formulate, questions that will require decades or centuries of study to address. What is the nature of this life? How did it originate? How does it differ from life on Earth? What can it teach us about the processes that drive biology, chemistry, evolution? Is it simple or complex? Single-celled or multicellular? Intelligent or merely metabolic? These are questions for the future. For now, the search continues, driven by curiosity, by the desire to know, by the recognition that understanding the universe requires understanding the planets within it, in all their diversity, in all their extremes, in all their strangeness. Every exoplanet discovered adds to the catalog. Every characterization refines our models. Every new technique expands the frontier of what is possible. The universe is vast, filled with hundreds of billions of stars, each a potential host for planets, each planet a unique experiment in the physics and chemistry of matter. We have only just begun to explore this diversity, to map the contours of planetary science across the galaxy. There are worlds out there that we cannot yet imagine, extremes we have not yet conceived, phenomena that will challenge our theories and force us to revise our understanding. And as we continue this exploration, as we push the boundaries of detection and characterization, as we build the instruments and develop the techniques necessary to study planets light years away, we are also, in a sense, studying ourselves. Earth is one planet among billions, one data point in the vast catalog of worlds. By understanding the extremes, by cataloging the diversity, we gain perspective on our own world, on the conditions that make it habitable, on the fragility of the biosphere we inhabit. We come to recognize that Earth is not the default, not the standard against which all other planets should be measured, but an outlier, a rare configuration of properties that, by chance or by necessity, has produced an environment where life can flourish. This recognition carries with it a responsibility, a recognition that the conditions we enjoy are not guaranteed to persist, that the stability of our climate, the thickness of our atmosphere, the strength of our magnetic field, are all contingent, all vulnerable to disruption. The study of extreme planets is, in part, the study of what Earth could become if certain thresholds are crossed, if certain feedback mechanisms are triggered, if the delicate balance that maintains habitability is upset. Venus serves as a cautionary tale, a planet that may once have been habitable but underwent a runaway greenhouse effect, transforming into the hellscape it is today. Tidally locked planets, with their extreme temperature gradients, remind us that day-night cycles, which we take for granted, are not universal, that rotation is a property that can be lost to tidal forces over time. Rogue planets, drifting through interstellar space, illustrate that planets need not orbit stars, that the architecture of planetary systems is not fixed, but can be disrupted, reshaped, torn apart by gravitational interactions. The extremes are not just curiosities. They are laboratories, natural experiments that allow us to test the limits of our understanding, to explore parameter spaces we cannot access through observation of our own solar system alone. They inform the models we use to predict planetary evolution, to simulate atmospheres, to calculate habitability. They provide the data necessary to move from a theory of planetary science based on 8 examples to a theory based on thousands, a theory that can account for the full diversity of worlds the universe produces. And this theory is still being built. The field of exoplanetary science is young, barely 3 decades old. The first exoplanet was confirmed in 1995. The first transit was observed in 2000. The first direct image was obtained in 2004. The first atmospheric spectrum was measured in 2007. Each of these milestones represented a breakthrough, a new capability, a new window into the properties of distant worlds. But each also revealed how much we do not know, how many questions remain unanswered, how much work lies ahead. We do not know how common Earth-like planets are. We do not know the fraction of planets that retain atmospheres over billions of years. We do not know the conditions under which life emerges, or how often it happens, or whether intelligence is a common or rare outcome of evolution. We do not know if the extremes we have discovered represent the true limits of planetary diversity, or if there are configurations, compositions, environments that we have not yet imagined, that lie beyond the reach of current instruments. They'll only be revealed by the next generation of telescopes and missions. But we are learning. Each new exoplanet discovered adds to the catalog. Each atmospheric spectrum refines our understanding of chemistry under extreme conditions. Each detection of a planet in the habitable zone raises the possibility that life exists elsewhere, that we are not alone, that the universe is filled not just with planets, but with biospheres, with ecosystems, with entities that look out at the stars and wonder, as we do, what else is out there. The extremes, in this sense, are not endpoints. They are waypoints, markers along the path of discovery, reminders that the universe is more diverse, more complex, more surprising than we anticipate. They challenge us to think beyond the familiar, to imagine worlds that bear no resemblance to our own, to accept that the universe does not conform to our expectations, that nature is more inventive, more resourceful, more capable of producing novelty than any human mind could predict. And so the search continues, driven not by the expectation of finding another Earth, but by the certainty that whatever we find, it will expand our understanding, it will reveal new aspects of the processes that shape matter, that govern the evolution of planets, that determine the conditions under which complexity can arise. The extremes are not aberrations. They're the norm. Earth is the aberration, the rare exception, the planet that, by a fortunate combination of circumstances, has remained habitable for billions of years, allowing life to emerge, to evolve, to produce beings capable of looking outward, of building telescopes, of asking questions about the nature of existence. This is the gift of exoplanetary science. It allows us to see ourselves in context, to recognize that our world is one among many, that the conditions we enjoy are not universal, that the universe is filled with possibilities we have only begun to explore. It humbles us, reminding us that we are not the center, not the pinnacle, not the inevitable outcome of cosmic evolution. It inspires us, showing us that the universe is vast, that there are worlds beyond counting, that the frontier of knowledge extends outward at distances we can barely comprehend. And it invites us to continue, to build the instruments, to analyze the data, to refine the theories, to push the boundaries of what is known. The extremes are waiting, scattered across the galaxy, each one a puzzle, a challenge, a question posed by nature and waiting for an answer. Some we will solve in our lifetimes. Others will require generations of effort, centuries of observation, technologies we have not yet invented. But the work is worth doing because it is the work of understanding, of mapping the diversity of the universe, of cataloging the forms that matter can take when subjected to the forces that govern planetary formation and evolution. The lava planets, with their molten surfaces and rain of rock, teach us about thermodynamics, about heat transfer, about the behavior of materials at temperatures that exceed the melting points of minerals. The tidally locked worlds, with their permanent day and night, teach us about atmospheric circulation, about the redistribution of heat, about the conditions under which liquid water can persist in narrow bands along the terminator. The hot Jupiters, with their supersonic winds and clouds of vaporized metals, teach us about fluid dynamics, about the chemistry of ionized gases, about the limits of atmospheric stability. The rogue planets, drifting through the void, teach us about gravitational interactions, about the chaotic early phases of planetary system formation, about the possibility of life in the absence of a star. The pulsar planets, orbiting the remnants of dead stars, teach us about survival, about the resilience of planetary systems, about the strange environments that can persist even after a star has exploded. Each category, each type, each individual planet contributes to the growing body of knowledge, the expanding catalog of what planets can be. And as the catalog grows, patterns emerge. Correlations between stellar properties and planetary characteristics, relationships between formation mechanisms and final configurations, trends that hint at underlying principles, at laws that govern the diversity of worlds. These patterns are still tentative, still based on incomplete data, still subject to revision as new discoveries are made. But they represent progress, the slow accumulation of understanding that characterizes all scientific endeavor. The universe is not random. It is governed by laws, gravity, thermodynamics, electromagnetism, quantum mechanics. And these laws constrain the possibilities, limiting the forms that matter can take, the configurations that planets can adopt. But within these constraints, there is immense freedom, vast parameter space, countless combinations of mass, composition, orbit, stellar environment that produce distinct outcomes. The extremes are the result of this freedom, the natural consequence of a universe that explores all possibilities, that produces every configuration consistent with the laws of physics. And we, as observers, as scientists, as beings capable of curiosity and reason, are privileged to witness this diversity, to catalog it, to study it, to attempt to understand the processes that produce it. This is not a task that will ever be completed. The universe is too vast, the number of planets too large, the diversity too great. But it is a task that will continue, that will drive exploration, that will inspire generations of astronomers, planetary scientists, astrobiologists to look upward, to build instruments, to analyze data, to ask questions. The extremes, in this sense, are not just scientific data. They are reminders of the vastness of the cosmos, of the diversity of phenomena that nature produces, of the limitations of human experience. They challenge us to think beyond the familiar, to imagine worlds that defy our intuitions, to accept that the universe is stranger, more varied, more capable of surprise than we can anticipate. They humble us, showing us that Earth, for all its beauty and complexity, is not unique, not special, not the center of anything except our own limited perspective. But they also inspire us, because they reveal that the universe is filled with worlds, that every star is a potential host for planets, that the diversity of environments is limited only by the laws of physics and the constraints of formation. They show us that the frontier of knowledge is open, that there are discoveries waiting to be made, that the work of understanding the cosmos is far from complete. They invite us to continue, to build larger telescopes, to develop better instruments, to refine our theories, to push the boundaries of what is known. And as we do, we will find more extremes, more worlds that challenge our definitions, more environments that expand our conception of what is possible. We will find planets that are hotter, colder, denser, larger, stranger than any we have yet discovered. We will find atmospheres composed of materials we have not yet imagined, surfaces shaped by processes we do not yet understand, orbits that defy our models of dynamical stability. We will find, in short, that the universe is more diverse than we thought, that the catalog of planetary types is far from complete, that the work of exploration has only just begun. This is the promise of exoplanetary science. It is not a promise of easy answers, of quick discoveries, of simple solutions to profound questions. It is a promise of complexity, of diversity, of endless variation, of a universe that rewards patience, curiosity, and rigor with insights into the nature of matter, the evolution of worlds, the possibilities of existence. It is a promise that, as we continue to explore, to observe, to analyze, we will come to understand not just the extremes, but the principles that produce them, the laws that govern planetary formation and evolution, the processes that determine whether a world is habitable or hostile, stable or chaotic, familiar or utterly alien. And in understanding these principles, we will come to understand our own world more deeply, to recognize the factors that make Earth habitable, to appreciate the fragility of the conditions that allow life to persist, to see ourselves not as the center of the universe, but as participants in a vast, ongoing process, a cosmic experiment in which matter, given time and the right conditions, can organize itself into forms of ever-increasing complexity, eventually producing beings capable of looking outward, of asking questions, of seeking to understand the universe of which they are a part. The extremes are not separate from us. They are part of the same continuum, the same spectrum of planetary diversity that includes Earth. They are, in a sense, our cousins, our relatives in the great family of worlds, each shaped by the same fundamental forces, each subject to the same laws, each a unique expression of the possibilities inherent in matter, energy, and time. By studying them, we study ourselves. By cataloging their diversity, we come to understand the context in which our own world exists. By exploring their extremes, we map the boundaries of the possible, the limits beyond which planets cannot exist, the conditions that define what it means to be a world. This exploration will continue for as long as we have the curiosity to ask questions and the means to seek answers. It will continue as we build the next generation of telescopes, as we develop new techniques for detecting and characterizing exoplanets, as we send missions to study the planets in our own solar system, learning from them lessons that could be applied to distant worlds. It will continue as we refine our theories, as we simulate planetary atmospheres and interiors, as we model the processes of formation and evolution, testing our understanding against the ever-growing catalog of observations. It will continue as we train new generations of scientists, as we inspire young people to look upward, to wonder about the stars, to pursue careers in astronomy, physics, planetary science, astrobiology. And it will continue because the questions are profound, because the implications are far-reaching, because understanding the diversity of planets is essential to understanding the universe itself. Planets are not just objects orbiting stars. They're the sites where chemistry occurs, where complexity accumulates, where perhaps life emerges. They are the environments in which the raw materials of the cosmos, hydrogen, helium, carbon, oxygen, iron, are transformed into organized structures, into atmospheres and oceans and crusts, into weather systems and tectonic cycles and magnetic fields. They are, in a very real sense, the places where the universe becomes interesting, where the laws of physics give rise to phenomena that are more than the sum of their parts, where matter, given time and the right conditions, can produce novelty. The extremes are the most striking examples of this process. The worlds where the laws of physics are pushed to their limits, where the conditions are so severe that only the most robust processes can operate, where the familiar breaks down and the alien takes hold. They are not comfortable worlds. They are not places we could visit, let alone inhabit. But they are worlds nonetheless, full members of the planetary community, deserving of study, capable of teaching us about the processes that govern all planets, including our own. And so the work continues, observation by observation, discovery by discovery, each adding to the catalog, each refining our understanding, each revealing new aspects of the universe's diversity. The extremes are waiting, scattered across the galaxy, each one a challenge, a puzzle, a question posed by nature. Some we will answer quickly, with existing instruments and established theories. Others will require new technologies, new approaches, new ways of thinking about planets and the processes that shape them. But all are worth studying because all contribute to the growing body of knowledge, the expanding understanding of what planets can be, how they form, how they evolve, what they can teach us about the universe. The journey is far from over. The catalog is incomplete. The frontier is open, and the extremes, in all their strangeness, in all their alienness, in all their capacity to surprise, remain the most compelling invitation to continue, to explore, to seek to understand the vast diversity of worlds the universe has produced.